Welcome to this crash course of the chapter Complex Numbers from your engineering semester 1. I've seen students misunderstanding this chapter as one of their most difficult chapters in semester 1. By end of this video, I'm completely going to change that perspective. You will not only have crystal clear understanding of every concept around this chapter, but you will be able to answer every question that comes your way with full confidence. This is the only video you need to score 100% in your upcoming university exam for every question for complex numbers. Let's get started. Let's first develop some fundamentals of this chapter. To start with, we'll start with different forms of complex numbers. Complex numbers can be represented in three forms. One is Cartesian form, other is polar form, and the third one is Euler form. Euler form is nothing but derived from polar form. We'll look at all those in detail. To start with, let's start with Cartesian form. To understand Cartesian form, let's say I have this x-axis and y-axis. Let's say this is my x-axis and this is my y-axis. In complex numbers, x-axis is also called as real axis. Y-axis is also called as imaginary axis. Okay, let's say I have a point in my first quadrant, which is x comma y. And let's say this point is z. Now that z is nothing but point x comma y, which is how we are going to represent complex numbers in different forms. If I want to write that z in Cartesian form, that z will be x plus iy, which will be the Cartesian form of complex numbers, where your I is square root of minus 1. I is square root of minus 1. Okay. And this form is called as Cartesian form of complex numbers. So always remember, Cartesian form is nothing but complex numbers represented in the form of x comma y. Okay. Complex numbers can be represented in another form, which is called as polar form. In order to develop polar form, let's say I have this origin. From origin, let's say I draw this line to z. I draw a straight line from origin to z. Let's say that distance is r. And let's say that angle that line OZ makes with positive x-axis, let's say that angle is theta. Okay. And let's complete that triangle too. Let's complete that triangle, right angle triangle. Okay. Now that R is also called as modulus of complex numbers. R is called as modulus. Theta is called as argument of the complex number. Okay, if you're writing the complex number in Cartesian form, it is represented with xy. If you're writing the complex number in polar form or Euler form, you write the complex number in the form of r and theta. So basically, if you want to convert from Cartesian form into polar form or Euler form, you basically convert that x and y to r and theta, where r is your modulus and theta is your argument. Okay, let's see how to convert that x plus iy in terms of r and theta. In order to do that, we know that this distance is x and this distance vertical is y. Okay, so let's say sine theta in this triangle. Let's try to calculate sine theta in that triangle. So sine theta is opposite upon hypotenuse, which is y over r. That gives you, so if sine theta is y over r, y is r sine theta, and cos theta is opposite upon hypotenuse. So cos theta is opposite upon hypotenuse, which is x over r. So which gives you x is r cos theta. Now, if you substitute those values in your complex numbers, you have basically converted your x and y into r and theta. So let's see what we get. We get z equals r cos theta plus I r sine theta if we substitute those values of x and y. Now, if I take my r common from these terms, I get r cos theta plus I sine theta. Now this is nothing but polar form of the complex numbers. Okay, I hope that makes sense. Remember that your R is called as modulus, and theta is called as argument. We'll look into those in detail in a second. But for now, remember that R is called as modulus and theta is called as argument of complex numbers. Also, this cos theta plus I sine theta, this term, cos theta plus I sine theta is also equal to e to the power I theta. You can easily prove that cos theta plus I sine theta is equal to e to the power I theta. So if you try to substitute that, you get R e to the power I theta. This is nothing but Euler form of complex numbers. So polar form and Euler form are both represented in terms of R and theta. Cartesian form is represented in terms of x and y. And that's how the three representations of complex numbers turn out to be. Now let's look at a modulus and argument in detail. So that R, which is the modulus, if you try to calculate R, the modulus from this triangle, you see that R, based on Pythagoras theorem, R is nothing but square root of x squared plus y squared. R is nothing but square root of x squared plus y squared. And in this triangle, if you try to calculate tan theta, which is opposite upon adjacent, so tan theta is y over x. Therefore, theta is tan inverse of y over x. Okay, theta or argument is tan inverse of y over x. Now, theta is where most students get confused. So I would like to give more detailed explanation on this theta because theta really changes based on which quadrant your complex number is. Right now, the complex number is in first quadrant. So it is very simple that theta is tan inverse y by x. Remember that this formula is only applicable in first quadrant for theta, okay, just for theta. This formula tan inverse y by x is applicable in the first quadrant. As the quadrant changes, there is a little bit tweak or change in that formula of theta. All right, now let's see how your argument or the angle that your complex number makes with positive x-axis changes based on which quadrant your complex number is in. Okay, we already saw in the first quadrant that your argument is tan inverse y by x. However, argument is not always tan inverse y by x. It changes based on where your complex number is. Let's see how. In all the cases, first of all, in all the situations here, we know by property of that triangle that theta is tan inverse y by x. That is for sure. In all the cases, the angle with the x-axis is always tan inverse y by x by property of triangle. Okay, I'll put mod of y by x just to be clear here because your y and x can be negative, but your theta cannot be negative here. Theta itself cannot be negative, so I put theta as tan inverse mod y by x. Now let's see what your argument. We already know in the first quadrant. Argument is equal to theta. Let's look at in the second quadrant. In the second quadrant, argument is nothing but angle that this line OZ makes with the positive x-axis. Okay, so with the positive x-axis, what is this angle from here to here? We know this whole straight line is pi, right? Whole straight line is pi. This is theta. So that pi minus theta is this leftover angle. So in the second quadrant, argument is nothing but pi minus theta, okay, or pi minus tan inverse y by x, because theta is tan inverse y by x. In the third quadrant, the angle that the line OZ makes with positive x-axis is this angle, all the way from positive x-axis to this line. So we know this is pi, this straight line is pi, and this is theta. So in the third quadrant, your argument will be pi plus theta or pi plus tan inverse y by x. In the fourth quadrant, this one, in the fourth quadrant, we know that uh, that line OZ makes with positive x-axis. We always go in anti-clockwise, okay? So it's from this side. We know this whole is 2 pi. This whole is 2 pi, 360 degrees. This is theta. So this is 2 pi minus theta. This angle from here to all the way here is 2 pi minus of that theta. So in the fourth quadrant, argument is 2 pi minus theta or 2 pi minus tan inverse mod y by x. Okay, that's how your argument changes as your quadrant of complex number changes. Note that theta doesn't change. Theta is always tan inverse mod y by x. But the argument is not always theta. Argument in the first quadrant is theta. In the second quadrant, it is pi minus theta. In the third quadrant, it is pi plus theta. In the fourth quadrant, it is 2 pi minus theta. So 2 pi minus of that theta. Okay, and theta is always tan inverse mod y by x. Now let's look at de Moivre's theorem, one of the most important theorems in this chapter, complex numbers. At least one problem you will get based on this theorem. Let's see what this theorem says. This says if you have cos theta plus I sin theta to the power n, it says that that can be written as cos n theta plus I sin n theta. So basically, de Moivre theorem states that you can multiply this power in the angle. That n can be multiplied in the angle like so. Okay. For example, if you have cos theta plus I sin theta raised to power 3, that can be written as cos 3 theta plus I sin 3 theta. A very simple theorem, but a very powerful one. Okay, that power can be multiplied inside the angle in case of cos theta plus I sin theta. Now let's say instead of this n, we have minus 1. Let's say cos theta plus I sin theta to the power minus 1. So this can be written as cos minus 1 theta plus I sin minus 1 theta, because that minus 1 can be multiplied inside. Okay. Now we know cos of minus theta is nothing but cos theta, and sine of minus theta is minus sine theta. So this will become minus I sine theta. So in other words, cos theta plus I sine theta to the power minus 1. This is nothing but 1 over cos theta plus I sine theta is cos theta minus I sine theta. Basically, if you have a reciprocal of that term, cos theta plus I sine theta, that can be just written as cos theta minus I sine theta. Okay, if we can extend this idea here as well. If we have z equals cos theta plus I sine theta to the power n, 1 upon z is, we know this is nothing but cos n theta plus I sine n theta by de Moivre's theorem. Okay, then 1 over z is cos n theta minus I sine n theta. If you take reciprocal, just this sign becomes negative. Okay, if you take reciprocal, that sign becomes negative based on de Moivre's theorem. A very simple theorem, but a very powerful one. Now let's try to look at this example from your Kumbojkar page 2-3 example 1a. It says prove that a plus ib to the power n plus a minus ib to the power n is 2rn cos n theta. Now remember, whenever you see powers in complex numbers, it's most likely de Moivre's theorem, because that's the idea of de Moivre's theorem, that power can be converted into this multiplication, like the n theta. So that power of n can be converted to n theta is what de Moivre's theorem is. Okay, let's start with that term a plus ib. If you see on the right hand side, you see r and theta. So most likely they have converted Cartesian form into polar form. We know that we know that a plus ib is r cos theta plus I sin theta. By converting it to polar form, we know a plus ib is r cos theta plus I sin theta. Therefore, we can say a plus ib to the power n is, we take n power n on both the sides. Okay, so a plus ib to the power n is r to the power n cos theta plus I sin theta to the power n. Okay, now we know by de Moivre's theorem, this can be written as, this is r to the power n, and this can be written as cos n theta plus I sin n theta. So now that's the first term that we got, a plus ib to the power n. Now let's look at the second term. Similarly, a minus ib is r cos theta minus I sin theta. Basically, you are just replacing that I plus I with minus I. So even here, you can just replace that plus I with minus I simply. So therefore, a minus ib to the power n is again r to the power n. Take r to the power n on both sides. Then you get cos theta minus I sin theta to the power n. Now again, applying de Moivre's theorem here, you get, just put that n in the angle. You get r to the power n cos n theta minus I sin n theta. Okay, so a plus ib to the power n is this, a minus ib to the power n is this. Now let's see your LHS is addition of those two, right? So your LHS, your left hand side is a plus ib to the power n plus a minus ib to the power n, right? Now a plus ib to the power n is nothing but, so a plus ib to the power n is this term rn cos n theta plus I sin n theta. So rn cos n theta plus I sin n theta. This a minus ib to the power n is rn, this term, cos n theta minus I sin n theta. Okay, we just substitute those terms. Now let's multiply that r to the power n inside. So we get rn cos n theta plus I rn sin n theta plus rn cos n theta. Multiply this inside, minus I r to the power n sin n theta. If you see, this term and this term will get cancelled, and you're left with rn cos n theta, rn cos n theta. That's nothing but 2rn, 2r to the power n cos n theta. That is nothing but your right hand side. So there is something further they ask. They say, hence deduce that 1 plus I root 3 to the power 8, 1 minus I root 3 to the power 8 is minus 2 to the power 8. Basically what they are doing is, instead of a they are putting 1, instead of b they are putting root 3, and instead of that n they are putting 8. Okay, so that's what we'll do. So since this is, instead of a they are putting 1, and this is b, and instead of n they are putting 8. Okay, so that's what we'll do. So we'll say again, since we know, we have already proved this statement is, we'll start with that. So since a plus ib to the power n plus a minus ib to the power n is 2r raised to n cos n theta. We have already proved this, right? So let's just say A equals 1, B equals root 3, and N equals 8. Let's put those values. So we get 1 plus I root 3 to the power 8 plus 1 minus I root 3 to the power 8 is 2R to the power 8 cos 8 theta. That's what we get, right? Now the only thing that we need to calculate is R and theta. So if you see here, we basically need to calculate now because this is our LHS. We just need to calculate R and theta. We know that R is square root of A squared plus B squared, and theta is tan inverse B over A. In fact, they also tell that in the initial question, they say this is clear that R is square root of A square plus B square, and theta is tan inverse of B by A. Okay, so let's see if we can calculate R and theta. So we know, which is why here square root of A square, which is 1 squared plus root 3 squared, which is square root of 1 plus 3, which is square root of 4, which is 2. And theta is tan inverse root 3 over 1, which is pi by 3. If you are not sure about how to do this, you can also use your calculator, but make sure it's in radians form. Okay. So we now know R, we now know theta. Just plug those values in your this equation that you have. So what you get when you plug in R and when you plug in your theta. Let me write my LHS first again. So 1 plus I root 3 to the power 8 plus 1 minus I root 3 to the power 8 is equal to 2R to the power 8 cos 8 theta. So 2R to the power 8. So R is 2. So 2R to the power 8 cos 8 theta. So cos 8 pi by 3. All right. So now you can just calculate that cos 8 pi by 3. Now cos 8 pi by 3, the way you calculate, you can also use your calculator anytime to calculate. But if anyone is curious just to calculate, this can be written as 9 pi minus pi by 3 to calculate that. Okay. And then you can say this is cos, split that 3 in both the terms. So you get cos 3 pi minus pi by 3. Okay. So now 3 pi, now if you imagine that angle, so this is 1 pi, then there is 2 pi, then there is 3 pi, and then there is minus. So it goes in the second quadrant. Okay. So if it goes in the second quadrant, this is negative, cos is negative. So this is minus cos pi by 3, right? And if it is minus cos pi by 3, which is minus cos 60, which is minus half. So this value is nothing but minus half. Okay. If that value is minus half, your final result will be 2 times 2 to the power 8 times minus half. So this 2 and this 2 will get cancelled, and you will be left with minus 2 to the power 8, which is your right hand side. Now remember that minus half, the way you can also calculate it using calculator. You don't have to follow this, which is why I have it in different color. You can directly use your calculator to calculate.